Well, I'm a student in my third final year of the bachelor degree, and I'm going to present you today the enhancement of indoor-outdoor classification with depth maps. Okay. First of all, my presentation contains an introduction in the domain of the problem, the original contributions, the computer vision and deep learning models, and a brief introduction in them. The data set we used, and the unsupervised and supervised experiments we performed, followed by the conclusions and future enhancements. First of all, I'm gonna show you a picture taken from space of a landform, and I'm gonna ask you what type of landform it might be, like is it a mountain or a valley? So we're gonna describe it a little bit. As you can see on the edges, we see that the color is much lighter and it's a bit softer, the terrain, followed by some cliffs in here, and in the middle we can see a bit more darker and more rougher terrain. Therefore, we could say that this could be a mountain range, for example. Now let's look at the next image, which is the exact same image but flipped upside down. And we can now see that within the way that we see the image at this angle, we could say that this is probably a valley, because we can see that there are some river banks, and this is actually the Grand Canyon. So this is the example of a problem that we encounter in computer vision due to the lack of information, and especially due to the lack of depth estimation that could have aided us a lot in processing these images. Another example could be this one, which is an Ames room. This is a famous illusion that makes people look tiny or giant depending on the corner of the room they sit in. So the room relies on our assumption that the rooms are perfectly squared with square angles, and we could not think otherwise of rooms. So making this assumption leads us on the wrong path, and therefore tricks us into thinking that these people have different heights. So again, when dealing with these type of images, from molecular images, we can rely only on geometrical cues that would help us understanding the scene, and not on exactly depth values, like real depth values. So we are going to ask now, how relevant are depth maps in the context of indoor-outdoor image classification? And for doing that, we're going to use an unsupervised Disney clustering algorithm that we are going to use on the DIODE dataset. And also the data that is extracted, the features that we extract from the images are going to be aggregated from different sub-images of different granularity. And to confirm the hypothesis, we're gonna test the features through, we're gonna input the features into an MLP classifier, and we're gonna compare the results in the end to see how correlated the results are. Okay, so in classic machine learning, someone would have to take the data set and process the features so that they would make sense to us, like consider information about the edges, semantic regions, and other information, other visual information. Now in deep learning and computer vision, we can now use end-to-end convolutional neural network that are better in this case, because we do not have any more to pre-process the data, and we can straight use the images. So in our experience, we've worked with the dense prediction transformers, or DPT, which is the current state of the art in computer vision and semantic segmentation and depth estimation. This is a direct improvement of the predecessor, the ResNest, which is related to the ResNet, which is a class of neural networks that are used as backbones for multiple deep learning networks today. Okay, so in what regards the architecture we used, we have for the same architecture for both the deep estimation and semantic limitation models. We input 384 by 384 models images in the model, and the encoder of the network will output feature maps of 49,152 features. And after the decoder, there are going to be 12.5 million features, which is pretty much, there are too many actually, and we are not going to discuss much on them because there are also, the computational cost is too high, and the performance is a bit worse than the one of the encoders, so we're gonna not include it in the future comparisons. So the image on the bottom shows the architecture of the DPT. It has multiple transformer blocks. The DPT that we use, the hybrid one, has 12 such transformers and the same number of fusion blocks. So on the decoder that are going to recreate the images for semantic limitation and depth estimation. However, we are not going to use the part from the head to for the parsing head onwards, because we are interested only in the transfer learning potential and the results given by the encoder. So the DIODE dataset has a lot of images that are pretty high resolution RGBD images. The D comes from the depth because they have depth maps. And the dataset has been collected with Faro Focus S350 laser scanners, which are very precise. They collect data with a precision of ±1 millimeter. And the benefit of this, I mean, the strong point of this dataset is that all the photos have been taken in a wide variety of environments over several seasons. So we can definitely be sure that the training will be thorough of the networks, and they will be challenged to perform tasks on this dataset. Also, apart from the RGBD images, as we can see on the middle row, there are also normal maps that depict how the angle of at which we see the objects from the camera. And these two, the normal maps and depth maps, could be used together to further improve the depth estimation. And one more thing that I have to mention is that the laser scanner has its limitation. It can scan up to 350 meters, and as you can see on the rightmost column, the sky is dark because it couldn't collect any information about the depth or the normals because the distance is too big. And also there are some problems with shiny surfaces or surfaces with high irregularities, like this bush in here that doesn't have a very good normal representation. As we can see in these histograms, we have the whole train set and whole validation set. The data is skewed towards the 0 to 50 meters interval, and from 100 to 300 meters, we cannot see anything because it's less than 1% of the whole data set. And also on the indoor train set, we can see that the data set, the distribution of data focuses mostly on the 0 to 10 meters. And however, there are some outliers on the 30 to 40 meters or so, because one reason to explain this could be that indoor images have some connections to outdoors, like windows, doors, and other glass surfaces, and the laser could see through them and record the data from outside. So there are some there is an explanation for this. And this is the outdoor train set and validation set that is not much different from the first distribution, because there are twice as many outdoor images compared to the indoors ones, because of the complex nature of outdoor environments and the need to have more in order to perform better on these tasks. So for the unsupervised algorithm, we're gonna consider the t-SNE with we considered it because it's a nonlinear algorithm, therefore being able to understand more and uncover more useful patterns in the data. And it uses the student T distribution, therefore the T in the t-SNE, that better disperses the clusters, because the T distribution is basically a normal distribution, but is less tall on the middle and taller on the edges, in order to treat more equally, let's say, the similarity between the points. Then the data we have, we normalize it by transforming with the inverse hyperbolic sign in order to increase the sensitivity to particularly extreme values. Also, the parameters that we used are perplexity, learning rate, and iterations. The perplexity refers to how clustered we expect data to be and how good a distribution of the data is. And 20 is not that much, because of our problem of binary classification, we consider the clusters to be pretty good and pretty clustered. The data should be pretty clustered together. And the learning rate is 3.0, because we want a learning curve to be smoother and to avoid local minima problems. And we ran it for 1,000 iterations. Okay, so in what concerns the automatic feature extraction, we considered RGB and RGBD images. We have feature vectors of 3 multiplied by k for RGB and 4 multiplied by k for RGBD, where k is the number of subsplits in the image. When k equals to 1, we consider aggregating the features from the whole image. If k is equal to 4, we split it into quarters, and if k equals to 16, we split it into 4 more quarters. Okay, so also for the DPT encoder decoder, we are going to consider it's being trained for semantic limitation and delta estimation to see how well the transfer learning performs for our task. In what concerns the problems, the tasks, the learning tasks we're going to face are the indoor-outdoor classification, which is a rather simpler one compared to the semantic limitation and estimation, but however, it's not to be neglected, because in these kind of very complicated and not so similar environments, there still are a lot of problems that we are going to encounter. The semantic limitation supposes that the algorithm learns to split the image into semantic regions that have meaning to us, like a wall, a building, some trees, and a telephone pole, as we can see on the image on the right, in the middle row. And also the depth estimation is no more a classification problem, it's a regression problem apart from those two. And it supposes that the algorithm learns for each pixel the depth value associated with it, and creates this kind of depth map that is whether of different shades of white and black, or it would use RGB data, like blue is the closest and then the red is the farthest away. Okay, so in what these are the first photos of clustering algorithms. These are the ones for the DPT encoder and the decoder respectively, trained for semantic limitation. As we can see, the clustering is pretty good. There are good boundary regions. There are not so many outliers, and we can confidently now say that the performances are good and the classes are separable. However, on the decoder, we can see that the regions are more clumped up, and there are some problems here with some outliers, and the boundary regions aren't that good. Therefore, as we mentioned before, we're not going to consider the decoder in future comparisons. Now, in what concerns the depth estimation, there are some problems here, probably because depth estimation is a different problem and learns different cues. Apart from the semantic limitation that learns the classes and tries to classify the regions, depth estimation learns more visual cues about depth, and it tries to classify rather depth than the classes of the images. And we also saw that the distributions are overlapped on the 0 to 10 or so meters of the indoors and outdoor classes, therefore making it difficult for the network to classify those. Okay, and here we have side by side the RGB and RGBD aggregated features. First, from no splits images, no splits, that means the whole image. As we can see on the left, the clustering is pretty bad. We cannot see a clear clustering. There are no rules, let's say. While when adding the depth information, we can clearly see that this clustering brightens up and the regions are better. However, there are some pretty big distances between the clusters, and that means that this is still going to have to be improved. Now for the four splits, we can clearly see that on the right, there's a better clustering. The regions are more compact, and this happens because when considering more features, we surely have a better understanding of more specialized context in the image rather than considering a whole image and supposing that the depth average it could be enough for clustering. However, the simple RGB clustering is pretty bad still because however it's we can see that a tendency for a region to be formed, and we're gonna see in the next cluster that it tends a little bit more to clump up together, but it's still pretty bad. However, when considering the depth information, we can now see that the clusters are more compact. However, the bounding regions are still not as good, especially apart from the four split, because now we have some problems with missing information. As we mentioned before, we have those black areas in the images, and especially for 16 splits, we are going to have entire sub-images that have no valid depth values, therefore making it difficult to compare to other clusters. So we consider that the four split could be the best, especially in the context of larger data sets where missing data could be a problem. And this table now shows the comparison between the RGB and RGBD processed through the multi-layer perceptron, and also the DPT encoder trained for depth estimation and semantic segmentation. First of all, we are going to consider mostly the area under curve measure for performance because we consider it to be more relevant than accuracy. So the AUC for the MLP RGB data experiments is pretty low. I mean, it's a bit higher than random guessing, but when adding the depth information, we can clearly see an improvement. And as we said before, the RGBD with four splits performs the best in this case. And also the DPT encoder does its best job here because the feature learned for the semantic segmentation help a lot in the context of indoor-outdoor classification due to the unique classes that define the indoor and outdoor settings. Like there won't be any cups or lamps on outdoor scenes or stuff like this. There won't be roads or trees inside mostly. So this could be a reason why the semantic segmentation performs better in this case. However, depth estimation is not to be ignored due to its performance on other data sets. And if we could figure out a better way to introduce the depth, then we could make further progress in this case. So the other future enhancements could consist of identifying more general features that could be used by both semantic segmentation and depth estimation models. These generic features could be then used by different models, and that would be adapted for other problems that they were designed for. say we could build one type solves all problems networks that we could just identify good features that could be okay with the more problems, a larger spectrum of problems, and apply train them for one thing, and then it could perform good in any situation. Therefore, our research on architecture transfer from semantic limitation towards depth estimation, in which we are performing experiments to better understand these general features and what could be of great use for us to solve multiple problems with a single network. Thank you.